today I want to walk you through the process of calculating the probability that the sample mean falls in a given interval. In order to do this, we need to remind ourselves of a couple of previously established facts. One, the mean and standard deviation of x bar are directly related to the mean and standard deviation of the parent population. That's the population being sampled from. And two, the distribution of x bar depends on the distribution of the population being sampled from and potentially the sample size. Recall that if the population is normally distributed, then for any sample size, x bar will be normally distributed. However, if the population we are sampling from is not normal, then we need the central limit theorem, which says for large enough sample sizes, the sample mean will behave approximately normally. Okay. And typically 30 is large enough. Okay. So that means if your population is not normal and your sample size is not more than 30, not only is x bar not normal, the central limit theorem doesn't apply, and the distribution will not even be approximately normal. Now, as long as either one or two apply, okay, so that is the population we were sampling from was normal, so x bar is normal, or if our original population is not normal, we at least have a large enough sample size that the central limit theorem applies and x bar is approximately normal. Okay. Then the process of finding the probability that x bar is between any two numbers, I'm going to call them number 1 and number 2 here, okay, is the same as finding the probability that any variable that was normally distributed fell between two numbers. Okay, so for us, this is the normal CDF function on our calculators. And we want our lower limit and our upper limit. That would be the first and second numbers. And then we have to tell the calculator the mean of our variable, which now is x bar. And remember, the mean of x bar is equal to the mean of the population we're sampling from. And the last thing we need to tell the calculator when we're working with the normal CDF function is the standard deviation of our variable. Okay, so the standard deviation of x bar is the standard deviation of the original population divided by the square root of the sample size. Okay, so once you have established that x bar either is truly normally distributed, or at the very least can be approximated by the normal distribution, then finding the probability that x bar is bigger than 3, less than 65, between 2 and 4, right, is a simple process of applying the normal CDF function on your calculator, tell it the range of numbers you're interested in, and then make sure you give it the proper mean and standard deviation for x bar. Now, I do want to remind you, though, that with any normally distributed variable, we can either adjust mu and sigma in the normal CDF, or if we wanted to, we always have the option of converting our normal distribution, in this case x bar, to a z-score. So we could take our two values, plug each one in for x bar, and we get two different z-scores, and that would be our new lower and upper limit. And then we would use 0 and 1 for the mean and standard deviation, because we've transformed our question into a question about z. Now, we don't have to do this. It's just always an option. Let's look at some examples. So you should remember this from the video on how to find the distribution of x bar. Okay, so all the problems in this video are going to be the same problems we started there. Okay, so we want to find the probability that the average amount of time it takes for 18 trips is more than 27 minutes. Okay, so we want the probability that x bar is greater than 27. To do this, we have to start with the population we're being sampled from. Our parent population is normally distributed. We know the mean and standard deviation of x bar will be equal to the mean that was given, 24.4, and the standard deviation that was given, 3.9, divided by the square root of the sample size, 18. Okay, so we know mu and sigma for x bar. What we have to determine is the distribution of x bar. as we just talked about. X bar is normal because the population we're sampling from is normal. So now we're just going to use our normal CDF function. We're going to draw the graph to make sure we get all our pieces in the right order. Okay, so I draw a normal graph. Okay, notice I've labeled the x-axis over here in the far right-hand corner, x bar, because that is the variable, right? And the average, the mu of the x bars is 24.4 because that was the mean of the individual loops. So that will also be the mean of all sample means of 18 loops. Okay, so we want the probability that the average is more than 27 minutes. So I've shaded everything in 27 and up. And now we need to find this probability. So again, normal CDF from 27 to infinity. That's our lower and upper limits. And then we need to tell the calculator the mean and standard deviation for x bar. Okay, so normal CDF, 27 to infinity. The mean of x bar is the mean of the population we're sampling from, which was 24.4. The standard deviation of x bar is the original population standard deviation, 3.9, divided by the square root of the sample size. So we get 3.9 over the square root of 18. And when you enter all that into your calculator, you should get approximately 0.0023. And that's all there is to it. The key is first establishing that x bar is normally distributed, and then making sure you adjust mu and sigma to be the right ones for x bar, not just the originals that were given to you for the parent population. Recall what I said a few minutes ago, that if something was normally distributed, we always have the option of converting to a z-score if we want to. So I want to look at the same problem we just did a second ago and find the probability the sample mean is greater than 27, which we already know is roughly 0.0023, right? So, but if we were going to do this by converting to a z-score, we would have to take x bar minus its mean divided by its standard deviation, and then we'd end up with a z-score. Remember this transformation of take a variable minus its mean, divide by its standard deviation, always gives you a new variable with a mean of 0 and a standard deviation of 1, and the shape is the same as the original. So if x bar is normally distributed, when we subtract the mean of x bar divided by the standard deviation of x bar, you get a normal distribution with a mean of 0 and a standard deviation of 1, which is exactly what z is. We had x bar of 27, so I'm going to plug in 27 for x bar and replace all the other values with their numerical values. And we end up with the z-score of 2.828. Okay, so a sample mean of 27 is the equivalent of a z-score of 2.828. We want the probability of getting this 27 or a larger x bar. So if we replace the 27 with something larger like 28, 29, 50 billion, right, we would end up with a z-score that's larger than the 2.828 we have now. So the probability of getting a sample mean that's higher than 27 is the same as the probability that a z-score is higher than 2.828. So now that I've converted to z-scores, I'm going to draw my z-graph, shade in everything to the right because we want to be higher than 2.828. We use our normal CDF, 2.828 to infinity. And because we've converted to z, the mean is 0 and the standard deviation is 1. And when we let the calculator do its work, you get 0.0023, which is exactly what we got before. Now, again, you do not have to convert to z-scores, but you do need to be aware that we always can when something's normally distributed, because there will be times when we do want to convert something that's normal into a z-score. In this problem, we're rolling a fair 12-sided die 19 times. So remember, the possible outcomes would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are discrete values, so the population we're sampling from is discrete. We want to calculate probably the average of those 19 rolls would be between 5 and 7. And those 19 rolls will be a sample. So we want probably the sample mean x bar is between 5 and 7. All right, to do this, we need to know the distribution of x bar. And that depends on the population that's being sampled from. Our parent population is not normal, again, because it's discrete. So when it comes to the distribution of x bar, we know the mean and standard deviation, right? But x bar here is not normally distributed because the population was not normal. It can't even be approximated with the normal curve because our sample size is only 19. So our original population is not normal and we have a small sample size. So this means we just don't know what the distribution of x bar is. So x bar is too unpredictable, okay, with our methods. It means we can't do this probability. So this problem would be over for us. This example is very much like the last one. We're rolling a fair, this time 6-sided die, 200 times. So again, it's a discrete population. We want to know the probability the average is less than 3.5. So I want to know the probability that x bar is less than 3.5. The population we're sampling from is not normal, it's discrete. Now, being a discrete population, you could go back to earlier in the semester. You could verify for yourselves that the mean is 7/2 or 3.5, and that the standard deviation of the die is going to be the square root of 35 over 12. So what about the distribution of x bar? Okay, we know the mean and standard deviation of x bar because they're related to the mean and standard deviation we just talked about from the original population and the square root of 200, the sample size. Okay, but the population we're sampling from is not normal, so x bar is not normal. The sample size, though, is 200. And 200 is large enough that the central limit theorem applies. So x bar is not normal, but it's close enough that a normal distribution and all the related tools we have, okay, we'll do a good job approximating what's going on with the average of the die. Not the individual rolls, but the average of 200 rolls. Okay, so we're going to draw the graph. We've got a normal curve. And x bar is the variable, so my legend over here in the bottom right-hand corner, x bar, those are the numbers on the horizontal axis. The mean of all the possible x bars is 3.5. We wanted to probably x bar was less than 3.5, so we're going to shade everything that is to the left of 3.5. Normal distribution means we get to use the normal CDF. And we want to go from negative infinity for our lower limit up to 3.5. And then we need to insert the mean and standard deviation for x bar, which are directly related to the mean and standard deviation up above. So normal CDF, lower limit negative infinity, upper limit 3.5. The mean of the x bars is the mean of the population we're sampling from, so 3.5. And the standard deviation of the x bars is the standard deviation of the parent population, square root of 35 over 12, divided by the square root of the sample size. So divided by the square root of 200. And you shouldn't be surprised when your calculator tells you that's 0.5 because this is a normal curve. 3.5 is the mean, and we want the probability that we are less than the mean. This graph is split exactly in half, and we want the probability that we're on the left half of it. So that's 0.5. Making sure we understand what this means. If we were to roll 200 times and get the average, there's a 50% chance that the average of those 200 rolls would be less than 3.5. I hope that you remember our discussion about attendance figures at Neyland Stadium being not normally distributed because every time the stadium was expanded, right, it created a new mode for attendance figures. So when we're asked what is the probability that the average attendance for 100 random home games is over 50,000, we're trying to find the probability that X bar is greater than 50,000. The population we're sampling from is not normal. So in terms of X bar, that means X bar is not normal. The sample size is 100 though, and that's more than 30. So even though the population is not normally distributed, okay, the central limit theorem gives us that X bar is close enough to being normally distributed that we can use it. That means we can use our normal CDF from 50,000 to infinity with the mean and standard deviation of X bar, which depend on the mean and standard deviation of the individual home games. The problem here is we don't know what those mean and standard deviation values are. So we can't figure out the mean of X bar and the standard deviation of X bar. So even though the sample mean X bar would be approximately normal, we can't find this probability. And it's not enough for X bar to be normally distributed. You also have to know the mean and standard deviation of X bar. We want to know the probability that the average wait time for 15 randomly selected UC patrons is less than 10 minutes. So we want to know the probability the sample mean, X bar, is less than 10. We know because we were told that the times you wait in line are skewed left. That is not a normal distribution. Normal distribution, first and foremost, is symmetric, not skewed. Okay. And that means the distribution of X bar is not normal. And when your population is not normal, X bar is not normal, you have to then look at the sample size. Our sample size here is 15. 15 is less than 30. So we do not know how X bar is going to behave. With such a small sample from a population that's not normally distributed, the values of the sample mean can be very unpredictable, okay, which means in this case, we can't find this particular probability. And for our final example, we're going to talk about painting the rock again. We want to know the probability the average number of people that took part in painting the rock in 5 random years is between 375 and 400. So we want the probability that X bar is between 375 and 400. The population we're sampling from, we're told, is normally distributed. So that means X bar will be normally distributed regardless of the sample size. So the sample size of 5 is not a problem. Now that we know X bar is normally distributed, we want to draw our graph. The mean of X bar, 381, is the mean of the population of individual years. 375 will be to the left, 400 to the right of 381. We're going to do normal CDF from 375 to 400. Insert the mean and standard deviation of X bar. The mean of X bar we already know is 381. So we're going to plug in 381 for the mean of X bar. The standard deviation of X bar is the original standard deviation, 47, over the square root of the sample size 5. Okay, so sigma of X bar is 47 over the square root of 5. And from there, the calculator does all the work. And we get a probability of approximately 0.4293. So that's how we calculate the probability that the sample mean falls in a given interval. We have to know that the sample mean X bar either is approximately normally distributed or legitimately normally distributed. And that depends on the parent population and the sample size in combination. And beyond that, we have to know the mean and standard deviation of X bar, which are related to the mean and standard deviation of the population we are sampling from. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!